My name is Mike DeLaCluse. I'm president of Lesman Instrument Company. I'd like to thank all of you for taking the time out of your busy schedules to join us for today's webinar, which is Introduction to Safety Instrumented Systems. Today's presenter is Bob Stahl. Bob is product specialist for Honeywell Field Products. Bob's been with Honeywell 28 years and has over 40 years of experience in electronics, communications, computer systems, and process control. Prior to working for Honeywell, Bob graduated from Purdue in electrical engineering and previously worked for U.S. Steel and K Instruments. Because we have a large number of attendees, we will be muting the phone lines. If you have any questions, please type it into the chat tool so we can respond. Bob, I'm going to turn it over to you.
Okay, thank you, Mike. And thanks for that introduction. So I'll get started with what I'm going to cover today. So I'll be talking about functional safety and what that term actually means when you compare it to safety in general. I'll talk about safety instrumented systems and safety instrumented functions and how the two are related. The other thing you'll see is that in safety, they're real big on acronyms. So you have SIS and SIF. I'll talk about the layer of protection analysis, which is how you determine what safety integrity level you need. So we'll find out what the safety integrity level is and how that applies. And I'll also talk about the risk reduction factor and how that relates to your safety integrity level. So this is more of a basic overview presentation. So I won't go into all of these topics in a lot of detail, but hopefully I'll give you enough background in all of them so you begin to get an understanding of what safety-related systems are. So if we look at what is safety, it's defined as freedom from unacceptable risk of physical injury or of damage to the health of people, either directly or indirectly as a result of damage to property or the environment. So just the first part of that statement, freedom from unacceptable risk, that pretty much defines safety to me. And we'll see next here what functional safety is. So functional safety is part of the overall safety of the equipment under control, sometimes referred to as EUC in the individual standards. And it depends on a system or equipment operating correctly in response to its inputs. So functional safety really means that the equipment operates the way you intended and keeps both your employees and the environment safe. Now, functional safety relies on active systems. So an example of functional safety would be the activation of a level switch that's in a tank when a high level has been reached. So that action would cause a valve to be closed, preventing the liquid in the tank from overflowing. Functional safety is achieved when every specified safety function is carried out and the level of performance required of each safety function is met. So there are two functional safety standards that we're mostly concerned with in the process industry, IEC 61508, and that's a standard written with intent to help design and develop products which are SIL rated for any industry. So for example, right now, Honeywell is coming out with a new version of our HC900 controller, and that will be SIL 2 rated. So the controller itself is designed to this particular standard, as would be sensors and final elements you'd use in the system. The other one is IEC 61511 and ISA 84.01. Now, they're almost identical standards, and they're written to help analyze, design, realize, install, commission, and maintain SIL loops for the process industry. So if you look at these individual standards, IEC 61508 is titled Functional Safety of Electrical, Electronic, Programmable Electronic Safety Related Systems, and 61511 is called Functional Safety Instrumented Systems for the Process Industry Sector. So 61508 is also referred to as an umbrella standard because underneath it is 61511 as well as a number of other standards that relate to safety in other industries or applications. So which standard would you use? Well, I touched on this a little bit, and for 61508, it's used to develop SIS devices like safety PLC hardware, embedded software in those devices, sensors and actuators. Where your SIS applications, which is what an engineer would do at a process plant, would be your process plant design teams, instrument engineers, system integrators, operating companies, regulatory inspectors, and so on. So that's kind of how the two standards are divided, where 61508 covers most everything. So what is a safety instrumented system? Well, a safety instrumented system, or an SIS, is composed of any combination of sensors, logic solvers, and final elements. So we'd see here a sensor, a logic solver, which in this case might be an HC900, and a final element. So the safety instrumented system is used to implement one or more safety instrumented functions. And we'll talk about the safety instrumented functions in the slides coming up. And any SIS is composed of any combination of sensors, logic, solvers, and final elements. It can include safety instrumented control functions, safety instrumented protection functions, or both. So what does an SIS do? Well, it's engineered to maintain safe operation of a process when unacceptable or dangerous conditions occur. An SIS must be independent from all other control systems that control the same equipment in order to ensure SIS functionality is not compromised. So you'll see here we have a process value that's running in a long time here. We have a normal process operation. And when we get beyond a high level there, we might get a high alarm level as shown on this slide where an operator could take action to make the system safe. If he doesn't do that, at some point the system will automatically shut down by the SIS. And then typically after that, there's also some sort of mechanical shutdown action, maybe a pressure safety valve, something along those lines to prevent this accident from occurring. If we look at types of safety instrumented systems, kind of the generic term for them is safety-related systems. That would cover all types. But you'd also see that we have safety interlocks, emergency shutdown systems, fire and gas systems, instrumented protective systems, burner management systems, and high-integrity pressure protection systems. Well, because of the systems I'm used to working with, of these, the burner management system is I'm probably the most familiar with. But the operation of many industrial processes involves inherent risks due to the presence of dangerous material like gases and chemicals. Safety instrumented systems are specifically designed to protect personnel, equipment, and the environment by reducing the likelihood or impact of an identified emergency event. So that's the object of putting a SIS in the first place. So when we look at IEC 61511, it has this layers of protection model. And you'll see each individual layer provides another measure of safety. Safety is provided by layers of protection. The layers of protection start with safe and effective process control. That's shown down here, starting with our process design. Then we have a basic process control system. The process control system itself provides significant safety through proper design of process control. The next layer of protection is also provided by the control system and the control system operators. Automatic shutdown routines in the process control system combined with operator intervention to shut down the process are the next layer of safety. And next, the prevention layer has the safety instrumented control system. And you'll notice that that safety system is independent of the process control system. It has separate sensors, valves, and a logic system. Its only role is safety. No process control is performed by the safety system. These layers are designed to prevent a safety-related event. If the event occurs, so we have process design up through prevention, and is to prevent an accident from occurring. If the event does occur, though, there are more layers designed to mitigate the impact, hence the name mitigation layer here. So the active protection layer, that may have valves or rupture discs designed to provide a relief point that prevents a rupture, large spill, or other uncontrolled release that can cause an explosion or fire. And after that, you have your passive protection layers. That might be a dike or other barrier that's around a tank designed to contain a fire or channel the energy of an explosion in a direction that minimizes the spread of damage. And then the final layer is your plant and community emergency response. So you'll notice that under the prevention layer, we could have an emergency shutdown safety system, which is separate from our process control system as shown here. The mitigation layer could have a pressure safety valve or a fire and gas safety system. So this is referred to as layers of protection or the LOPA model. So what is a safety instrumented function? Well, the safety instrumented function looks kind of like a safety instrumented system, and that's because your system is made up of individual instrumented functions. So a function has a sensor, logic solver, and final element, as shown here. So the safety instrumented function has a specified safety integrity level, which is necessary to achieve functional safety. The SIS sensors, logic solvers, and final element act in concert to detect the hazard and bring the process to a safe state, which is the whole point of our safety system, is to, regardless of what happens, bring the process to a safe state. So if we look at the safety instrumented system, it actually consists of multiple safety instrumented functions. In my case here, I have 3 individual SIFs that are in this one system. And you'll notice we have different sensors. We have a pressure sensor that operates the valve based on what sort of logic we have in our logic solver. And the logic solver, that could be a PLC. It could be a hybrid controller. For example, it could be an HC900. And in my case, that happens to be the product that I support. So we have dual temperature transmitters here. making up another safety instrumented function, and then a flow transmitter here that makes up another safety instrumented function. And in this particular case, the sensors all have an effect on one final element. You'll see in a lot of cases, though, there are actually multiple final elements depending on the needs of the safety system and the individual SIL level. So what is SIL? Well, that stands for Safety Integrity Level. It's a quantifiable measurement of risk used as a way to establish safety performance targets for safety instrumented systems. Probably the most important thing to remember is a SIL rating applies only to the instrumented function that we showed here on our previous slide, right? We have our instrumented functions here. So when you have a SIL rating, that doesn't apply to your overall system. It applies to the devices that make up the safety instrumented function. And the safety integrity level, there are 4 levels. So we have SIL 1 through SIL 4. And each of these corresponds to a range of target likelihood of failures or probability of failures of a safety function. And as I said, note that a safety integrity level is a property of a safety integrity function, not of the overall system. And once again, IEC 61508 is where we get this individual safety information for our SIL level. So the objectives of SIL analysis are really a number of them here. Personnel safety, primarily, I would say, protection of equipment, protection from litigation, profit, because if your system is safe, it remains running, hence you can make more of that product. Also environmental safety, so we maintain the environment around the plants and are good neighbors to the rest of the community. So here you see we have a SIS and a VPCS. That just stands for Basic Process Control System. And as I said, this safety business is full of acronyms. So here, Basic Process Control System is how you would refer to the system that normally creates, I should say, controls your process. The SIS system is totally separate, and that's the safety system for your process. So there's another drawing of a separated solution where we have the basic process control done by this single loop controller, in this example using these sensors and valves, where our SIS has a totally separate sensor and valve that are in the same line. So if the process control system fails totally, the SIS can take over and make the system safe. So everything regarding these safety-related systems really applies to the risk involved. And what we'll see is, as we look at our systems and go through them, we're going to determine how much risk we can allow in a particular system. And risk is defined as the combination of the frequency of occurrence on the left side of the graph here and the severity of that harm. So you remember at the beginning of the presentation I said that safety is freedom from unacceptable risk. So here we'll define what risk is as related to process control systems. So when we have an unacceptable risk, we either have too many occurrences of an incidence of harm, or the severity of even a low number of a particular incident would still give us too high of a level of harm. So as I said, risk is based on the frequency and severity of consequences. So if we look at air travel, and we have a plane crash, in this particular crash there were 200 deaths. So we say that once in 20 million flights globally per year, okay, so that the probability of that is 1 time in 20 million, or 5 times 10 to the minus 8. 1 in that many flights will have an accident. And in that accident, the severity was 200 deaths. So if you multiply these two together, there we come up with our safety risk. So it's, once again, it's the severity times the frequency. That's what gives us our safety risk. So for a car crash, we might have 1 car crash in 1,000 road incidents that causes 2 deaths per year in a large city. Now you notice the frequency is defined as per year in both of these cases, and you'll see we use that as we go along. So once again, it's 2 times our probability, which is 1 in 1,000. That gives us a safety risk that's higher of 2 times 10 to the minus 3. So this is how we calculate a risk for a process control system as well. Now the way that's done is using a study called a HAZOP, or Hazard and Operations Study, Operability Study, rather. So a HAZOP assesses the risk associated with a hazard that might be part of your process in, say, a chemical plant. It's a structured and systematic examination of a planned or existing process or operation in order to identify and evaluate problems that represent risks to personnel or equipment or prevent efficient operation. So it identifies and evaluates problems with a process, risks to personnel or equipment, potential operability problems, potential deviations from the design intent of the system, and it will also look at possible causes of deviations and assessment of the consequences of those. So a HAZOP's more of a qualitative versus quantitative technique, and it's based on guide words and is carried out usually by a multidisciplinary team of operators, engineers, other employees during a series of meetings, and they're referred to as a HAZOP team. So there's also an IEC standard for hazard and operability studies, or HAZOPs, and so they're shown here as my IEC standard for that, 61882. So if we're going to compare the HAZOP versus our SIL rating for a system, that would be for a function, I should say, actually, right, because the SIL rating is for a safety instrumented function. We'll see that the HAZOP covers their process equipment, process control system, alarms, and operator interaction, where the safety instrumented system has a particular SIL rating for that system. So how do we develop our risk reduction that we need? Well, another tool that's used as part of this safety analysis is called a layers of protection analysis. It's a widely used risk assessment technique, and it can be viewed as an extension of HAZOP. So typically you would do the HAZOP first, and then do this layers of protection analysis. It's a simplified risk assessment method, and it provides a method for evaluating the risk of hazards and comparing it with risk tolerance criteria to decide whether your existing safeguards are adequate or whether you have to put more safeguards in a system like an SIS. It's a semi-quantitative risk analysis tool, and it determines something called our risk reduction factor. So after we go through the HAZOP and go through this layers of protection analysis, we should come up with what sort of risk reduction you need for the particular system. The LOPA is a semi-quantitative risk analysis, as I said. And using a LOPA is consistent with the requirements of our IEC 61508 and 61511 standards. So now we actually get to our SIL determination. And remember that the SIL determination applies to our safety instrumented function. And we'll calculate the SIL level for our entire safety instrumented function. We'll see that coming up. So from the HAZOP risk matrix or the LOPA risk table for your particular application, now that would be your process plan. Remember, we said that risk is the frequency times severity, and we have this risk matrix. So we'll see here along the left side we could have one incident per year, which would be one serious injury in 1 year, or one serious injury in 100 years, or one serious injury in 1,000 years. So if we say that our present risk is 1, we're in this H1 quadrant, where we would have one serious injury in 1 year, and we want to get to, naturally, this low quadrant that's green, which is one injury in 1,000 years. The risk reduction factor we need is 1,000 for this system. So that gives us our overall risk reduction factor that we need for the system. So if we look at the system, we have our present risk, which is one serious injury per year here. And we want to go from our one serious injury per year down to one serious injury per 1,000 years. And once again, this EUC is equipment under control, or our process system. And so we need this particular risk reduction, and we said our risk reduction factor is 1,000 from the information in our HAZOP and LOPA. So our actual risk reduction comes from risk reduction by external risk reduction facilities, our safety-related system, and that says partial risk covered by electrical, electronic, or programmable electronic safety-related systems. You also have partial risk covered by other technology safety-related systems. For example, the basic process control system we saw provides a certain measure of safety. So from that, we come up with our risk reduction that's achieved by all the safety-related systems. Now that brings us to safety integrity levels, or SIL. So you remember back earlier I was talking about SIL levels, and we said that the SIL levels are 1 through 4. And you'll notice each level corresponds to a particular risk reduction factor. Now, if you look at the risk reduction factor and the SIL level, they correspond. as well as the reliability of your safety functions, and your probability of failure on demand. And probability of failure on demand is a term you'll hear a whole lot when you're talking about safety systems, because that indicates the probability of a system failing to respond to a demand. And by demand we mean, okay, the system has to react because we're getting into an unsafe state. The average probability of a system failing to respond to the demand in a specified time interval is referred to as PFD average, which is what you see here. So in this case, we say that our probability of failure here is 10%, here it's 1%, here it's 0.001%, and here it's 0.001%. So a SIL-4 system would be rated greater than 99.99% reliable. So as far as the process industry goes, we're really only concerned with SIL levels 1, 2, and 3, though. Those would be the only 3 levels that we're concerned with in the process industry. So the PFD average, that's also called the probability of a dangerous failure. That may make more sense to you than failure on demand. And our safety-related system will usually implement more than one safety function. So let's take a look, now that we've seen what the 4 SIL levels are and how we decide which SIL level we need for our particular safety function in a system. We can take a look at the standards compliance. And our target SIL must be specified for each SIF based on hazard and risk analysis. So you'll note once again their SIL only relates to a safety instrumented function. And remember, we can have multiple safety instrumented functions in one safety instrumented system. The safety of a system also has a life cycle. They refer to it as just that, the safety life cycle. And so you must have processes established for the safety system so that it's tested at a particular interval and so on. Each SIF must meet the target SIL requirements for the random failure rate, once again, which is this probability of failure on demand average, which is over a certain period of time. That's called the test interval. You also have architectural constraints in the system and the development process for each component. In other words, each component has its own SIL rating. So let's take a look at a couple of systems. So here we have a system that's a single sensor, a logic solver, and a valve. So if this is a safety system, we can buy sensors that are SIL rated. The rating on the individual sensors, or in this case on the logic solver, are typically done by TUV. And so when you get one of these devices, it'll have a certificate that comes with it that says it is certified by TUV and what the particular SIL level is. So for a given SIL level, for example, for the sensor, our probability of failure is 0.005. And for the logic solver, it's 0.005, which would be a SIL 3 rating. 0.005 is our SIL 2 rating. And then you'll notice the valve actually has the lowest SIL rating with a 95% reliability in this case. So the SIL calculation for the overall SIF is the sum of these individual probabilities of failure. So what we come up with in this case is 0.0555, or 5.55% would be the probability of failure. So the system would be a little over 4% reliable. And since the risk reduction factor is the probability of failure average, the risk reduction for this system happens to be a little over 18. So if we look at another example, we'll see that we have another sensor and a logic solver, and this time we've put two SIL2 valves, two valves that have the 005 rating, like we see on this slide, right? We have a SIL1 valve. So if we put two of these valves in series and we multiply their probability of failure, we come up with 0025. So our PFD average for this system then becomes 0008, which falls under the SIL2 range. So in other words, this particular system, this safety instrumented function, would be 99.2% reliable. So here I've given you really a broad brush overview of how a safety system is defined and calculations are done for it. So Mike will let me know what sort of questions have come in here.
Bob, believe it or not, I'm not showing any questions. Maybe we'll give it a minute and see if any pop up.
Okay.
There's a question for the audience. There's a question tool associated with the little control bar. So if you do have a question, please type it in and we'll get it answered. First question has come in. Do these standards and ratings only apply in the U.S.?
No, the IEC ratings are actually worldwide. You have different standards like ISA 84 that was developed primarily in the U.S. But the certification group that Honeywell uses is actually in the Netherlands, and that's who developed our SIL3 rated controller, which is known as a safety manager. So applies worldwide.
Okay. Next question is, can we get a copy of the presentation? I'll partially answer that by saying that we are recording this presentation and it will be posted back out to our website for future replay. And everybody that's on this will get notification when that's posted. Bob, I don't know if you want to share a copy of your presentation or not. That's up to you.
Yeah. A PDF copy of it, I can do that.
Okay, so why don't you give me a PDF copy and I'll post that as well.
Okay.
Let's see. They're now rolling in, Bob, so we're we're just going to get to keep going on the questions.
Sure.
What are the steps to get a customer involved in a HAZOP?
Well, a customer would be, if a customer already has a system, like we'll say it's a chemical plant or a petrochem refinery, whatever that may be, they're already doing HAZOPs or something like them because they're required by OSHA. So they go through that particular exercise just to maintain the safety of their facility, and also they're required to do that by law. That's the best answer there. I don't know that you'd necessarily get a customer involved in one unless they already knew they had a safety issue.
All right. The next question is, how did you come up with 18 in the one example?
Okay, if I go back to that for a minute, if we look at the probability of failure overall, okay, on the first one, if we look at our system, our single system here, we come up with 0.0555. Right? Now the risk reduction factor is just 1 over the probability of failure on demand. So when I do my math, if I do it right, I come out with, when I take 1 over that particular percentage, that value I should say, that's what gives me the risk reduction of 18. Now the second system that uses 2 of the valves, there we came up with a PFD average of 0.008, and in that case our risk reduction factor would be 125. So that it's simply 1 over. Okay.
Okay. How do systems like Experian differentiate aspects of, it says BMS, from standard control? So burner management, I'm assuming.
How do systems like Experian? Well,
yeah, differentiate aspects of burner management from standard control.
Well, they actually would be 2 separate systems. For example, the Experian system might be doing the process control, and whatever you had for a safety system, which could conceivably be another SIL-rated controller, right? So if they have a controller that's SIL 2 rated, the important thing is that one device does not do both the process and the safety portion of a system. So by device there, I would mean a SIL-rated controller. We have SIL-rated sensors, valves, and controllers. So a system like it.
The 7800 series, if you put one of those little controllers in the burner management system, they have a SIL rating as well, don't they?
Yes, that actually has a SIL 3 rating.
Yeah, that's what I thought.
Yeah.
All right. Can wire routing affect the SIL rating of an SIF or SIS?
I can't answer that one directly. I don't have enough knowledge. I would say that the wire routing, let's say, the wire routing would affect whether your safety system is going to fail or not. Wouldn't necessarily affect the overall SIL rating because it's not really a quantifiable measure. But I'll have to leave that question for another time, or I could get an answer to that question if I have the person's email address.
Okay, we've got it.
Okay, because we have, I'm not a process safety expert. I'm an expert on the HC900 controller. We have people in Honeywell that are functional safety experts, and that's all they do. And when they do safety work on systems, they use software packages that develop all of the individual components of a system and calculate the reliability of those systems. So I don't like to make things up, as you know, Mike. So
next question. If a plant is running for a long time without any SIL study, then how do you sell this idea to management, even to explore the benefits of SIL? I see a lot of lack of knowledge in this area, and just curious.
Well, I would have to go back to my original answer where he said that particular plant we'll say that if a plant isn't abiding by the OSHA rules, eventually they would be cited. And at that point, they're going to decide they have to do something about safety. You know, that kind of thing usually happens after some sort of fatality. I mean, I worked in the steel industry for a long time, and that's when you would see the most action regarding safety, was when someone was hurt or killed, right? So the idea here is to determine the overall safety, have this safety life cycle, and that safety life cycle has to be managed, and I refer to that as safety management. So I don't know that you would necessarily have to sell anyone on the idea, you know. And the object here, the idea here is that as I showed back on one of my earlier slides, the basic reasons you put in a safety system is these objectives of a SIL analysis, you know, personnel safety, protection of equipment, and so on. So if you're running a company, you need to protect your equipment as well as your employees. You have to do that in some manner or another, or eventually you're going to kill someone or destroy your plant. I guess that's the best answer I can give you.
Pretty good reason to do some safety analysis.
Keep your name out of it.
Yeah, stay out of the newspaper. That's what all leaders of companies want to do. On a P&ID, is the difference between a high alarm and a high alarm that between the BPCS and the SIS system?
No, the high alarm and high alarm are actually all part of the basic process control system. When you get above that high alarm level, like when you get to the high alarm level, if everything is working right, it should shut the system down. And, you know, your basic process control system, that's where your safety portion of the process control system comes from. Now, if that fails, for whatever reason, I mean, you've already got your high alarm, the operator didn't respond to it, you got the high alarm that was supposed to shut down the system and didn't, and then at that point is when the safety system comes into play, and it should shut down the process through its separate means in order to maintain the safety of the overall plant. Right?
All right. The next question, can the safety controller and the process controller be the same device?
No. We'll say that, let's say I had two HC900s. I could configure one of them as the process controller, and we have actually within an HC900 we have two ways that it can be programmed, one for process and one for safety. So you could think of it as two different worksheet types that either allow operation as a safety system or as a process system. But the two systems still have to be separate.
Yeah. So
otherwise they would have what are called common cause failures.
Right. So they can be the same type of controller, but they cannot be the same exact controller.
Right.
As long as that series of controller has a accelerated controller as part of its offering.
Right. As long as your safety controller does have a SIL rating.
Correct. Right.
Yep.
Let's see. The next question, which I'll respond to an email. We talked about the Honeywell burner management equipment, and he asked us to email some of the latest part numbers, model numbers for those applications. I'll go ahead and do that, but just to repeat, it's the 7800 series of Honeywell burner management systems. The last one is just thanks for the answers and the great informative session. Season's greetings to all. Very appropriate.
Yes.
Bob,
Merry Christmas to you as well.
Yeah, Bob, thank you very much for your presentation. If anybody does have any specific questions, feel free to give me a call. Best way to get a hold of me is 800-9-LESMAN or 800-953-7626. My email address is also MikeD, M-I-K-E-D, @lesman.com, and I'll make sure that Bob and I get coordinated and get your questions answered. At this point, if there are no further questions, the session is concluded. Thank you very much for attending, and thanks for spending the time with us. Bob, thanks for the presentation. Merry Christmas, Happy Holidays, season greetings.
Yep. You're welcome. My pleasure.
All right. Thanks, Bob.
Thank you.
Bye.
Bye-bye.